I'm Nini Xie. I work for the University of Toronto, and welcome to the morning session of ICFP on effects, one of my favorite research topics. And we have 3 talks in this session, and we will have a Q&A at the end of each talk. And for people from the audience, you can ask the questions at one of the mic places, and you can also ask the questions through Discord. We have paper-specific threads on Discord for each of the talks. And our first speaker of this session is Filip, and he will talk about a fine-grained reduction theory for effect handlers. So yeah, please take it away.
Thank you very much, Ning Ning. Yes, my name is Filip Sieczkowski, and this is joint work with my colleagues Dariusz Biernacki and Mateusz Pyzik over at the University of Wrocław. So, yes, as you can see, the title of the talk is a general fine-grained reduction theory for effect handlers. And so there might be some words in the title that are more clear than others for different people, different words, presumably. I would like to start with talking a little bit about effect handlers, so what they are and how they work. So what they are is this new and increasingly popular way of structuring computations with effects, so effectful computations. So I have here an example snippet of a program, right, with several colored in things. So we have these operations here in red, ask and tell, and the idea is that these denote some effects that our program can make, or operations that can appear in the program. And the core idea, I suppose, from the operational point of view of how these operations work is they don't have a meaning associated with them at this point, at the point where they appear in the program. So what they say is, okay, I'll pass the control somewhere else, and that other part of the program where I pass control, I might not know where it goes to just yet, it will tell me how to interpret the operation at that point. Right? So the other part, so these are the effects, the operations, the other part is the handlers. And the handlers are what gives semantics to matching operations. So here we have an ask operation and a matching handler for that operation. And we also have a tell operation, which in this snippet of code is not, is not interpreted. Right? And then the idea is it looks a little bit like exceptions. It generalizes exceptions because the control can return to the call site. So the handler for ask here, it says, well, I'll get asked to provide some value, and I will get an access to the resumption, which represents the part of code between the ask and the handler. And then I can pass the value back. So this is what will happen. So the idea is, it's simple. We have some iteration through the list, 1, 2, 3, with a function that first asks for some value, and then the idea is it tells another value, right? Computes some other value and tells what the result should be. So we can easily see that this program will or can compute at least part of its output. Now, one of the things that I've mentioned already is the tell operation is not interpreted in this snippet of code. So the idea is if we start to just simply try to reduce, capture part of the context, pass it over to the handler, continue evaluation, we'll eventually reach a program like that. And this program in this simple view is stuck, right? Because we only have a partial program, and this can happen when we're, I don't know, trying to optimize program, partially evaluate it, trying to find, fully reduce the program, find a normal form, this sort of stuff. And the idea is, well, we hang on an operation, we have a tell, and we don't know what to do. And the most of the popular semantics, operational semantics for effect handlers, at this point, they would get stuck. So they are very nice for actually running, completely evaluating fully closed programs where all the all the operations will be interpreted and there will be no free variables, nothing like that. But in an open context, they get stuck in a place that's not necessarily brilliant, because, I don't know about you, but this is not the sort of normal form that I would like for this computation. Right? There's still something that could be could be hopefully evaluated. There's all sorts of iteration over the second list, right, the smaller list. So the idea is then, well, can we do better? Because this is not great for program optimization purposes, for instance. And in fact, we can. And so in the paper, we build on some of our earlier work in other control operator contexts, where we found out that we can give semantics to delimited control by looking at how the delimiter, in this case the handler, interacts with computation formers. So the idea is, and this is a slightly different syntax here, so how does interaction of the handler with various computation formers behave, right? So what do we have? Well, we can have a computation that's just a value. We can have a computation that is some sort of an operation here called do. We can have a computation that's formed by sequencing through let expressions, right? And we can have a computation that is some other operation that the handler does not know about. So the tell in the example before, and this is expressed through the lift. And I will not go into too much detail about the do and lift. There's some interesting stuff going on there, but you'll have to see the paper start. So, okay, so how do the interactions behave? Well, the interaction of a handler with a value, it behaves in the same way that most effect handler literature does it. So you basically just say, well, I have my handler, here the underscore, and I have something, some computation that I'm supposed to do after I finish with the return value. So, okay, simply just pass the value to the return clause and go ahead. Now, the second part of the interaction, this can be viewed as a sort of optimized version of the usual reduction rule for deep effect handlers for a particularly trivial context between the operation and the handler. Now, this is nice. It's short, and you don't really capture very much of a context. You don't need to reify it as a value. That's all nice, but not all contexts are like that. And the idea then is, well, we will get to the point where all the contexts look like that by successfully eating the intervening context. So successfully looking at how the handle interacts with the let expressions mostly, so with the other computation formers. And in the rule for the handling interacting with the let, what we see is that the handler gets duplicated. So for those of you who know about these things, this is what makes the reduction, the handlers behave as deep handlers, right? Because the idea is, no matter whether the do appears, whether the operation appears in E1 or E2, it will be handled by the same handler. See here, the H, the handler, the body of the handler, what says how the operation will be interpreted, is repeated. So both will be interpreted in the same way. And then finally, if our operation does not match the handler, well, then we simply sequence a computation, and nothing in particular particularly interesting happens. And obviously, for full picture, there's also some other boring reduction rules like beta reduction. Who needs that, right? So, okay, so let's take a look at this set of rules. For now, it's just a set of rules, arbitrary, and look how it behaves if we start from the point where we got stuck last time, right? So this is the same computation we saw the slide before, and here we see that we have an operation that doesn't match the handler. But it's not really in the evaluation position. We start with a sequencing operation, right? So there's a let somewhere, a little bit hidden by the semicolon. So what happens is the handle first interacts with the let and gets duplicated. And see here, it gets passed to the continuation of the tell operation gets passed to the return clause of the handler and wrapped inside the handler. And what we can see here is that this part, this duplication, is what will allow us to reduce further and further and further going forward, right? So this we can sort of believe that this will possibly eat the entire list, iterate through the entire list. But first, what happens on the outside? Well, the handler doesn't match the tell operation. So what happens is we simply sequence the return clause, the body of the handle, with the tell 6. And we get a nice simple tell operation just hanging there and waiting for the handler, because we still don't know the handler for it. And so in the end, we get this sort of normal form, what we see below. And to my mind, at least, this is much better than what we had before. But, you know, obviously, this means we're all set. This is all fine. It worked on the one simple example, chosen by me. So obviously, everything's fine, right? Well, not necessarily. For now, it's just a set of reduction rules. Who knows what sorts of reduction theory they encode? So the question that I would like to ask is, what makes a reduction theory a good reduction theory? And to my mind, there's two angles here. On one hand, it's the properties that the reduction system has. On the other system, it's applications. Now, as it happens, a set of reduction rules very similar to this one, slightly different setting, but very similar in spirit to this one, was already considered, I think, at ICFP a year or two ago, as a means of program optimization. So, okay, this could increase our confidence a little bit, because, okay, that's two sets of people coming from different directions looking at a very similar set of rules, right? But another part of what makes a reduction theory interesting or good is what sorts of properties it satisfies. And the properties, well, that I would say are the ones that would make this reduction theory interesting and good for deep effect handlers is firstly confluence. So, you know, we can, if we reduce to two different sub-expressions by reducing in different parts of our expression, we can always go to the same answer. And the second one, so this is the proof is mostly standard. There's a lot of critical pairs, but other than that, there's nothing much going on. So you'll have to look at the paper if you want to see the details. But the second part is standardization, which is quite tricky. And I will try to tell you a little bit about how this works. And then obviously, you know, right now we have some sorts of reduction theory. Maybe we will have some sorts of evaluation relation based on that reduction theory. But that's fine, but how does it relate to the sort of traditional reduction that we started with? And if I have some time, I will be able to show you maybe a little bit about that. And then in terms of applications, what we also did in the paper is based on this reduction theory and the nice normal forms that it produces, we managed to build a semi-algorithm, obviously, because without types, it's not guaranteed to terminate, for full normalization. So, NBE-style algorithm. Okay, so what is standardization even? So the idea is, this is one of these old big open problems in lambda calculus, right? If I start reducing, if I have a sequence of reductions sort of happening anywhere in the term, right? So the sequence here in black, then the idea is for any such sequence, I can sort of split it in two subsequences. First, an evaluation sequence that will proceed to some point, not necessarily to a value. You know, this is any sequence that there might be no reductions at all. And then a sequence that follows that of internal reductions. Now, so far so simple. You know, we can take the evaluation to be identity and everything's fine, right? But in order for it to make some sense, we want to impose some conditions on both the evaluation relation and the internal reduction, which is what happens in the second stage. And to my mind, the sort of defining properties for these are that the weak head or evaluation relation does not go under binders, which is probably what most of us would class as evaluation, and that it is deterministic, not necessarily in the construction itself, but in the location of the redex. And the internal reduction, like in contrast, it always preserves the top-level constructor, and generally speaking, it only allows internal reductions itself in the evaluation position of every construct. So it's sort of very constrained in terms of how the shape of the term can evolve, right? So that it doesn't do too much, so that we are forced to do the things that we can do as evaluation in the evaluation stage. Okay. This has been solved for lambda calculus some 50 years ago, and in the last 20 or 30 years, there was a lot of interesting work on making the proofs much nicer, because this used to be a very tricky problem, and the early proofs of this are pretty ghastly to look at. So, okay, yeah, there's good methodology, well developed, just roll it out and everything will be fine, right? Well, not quite. There's these critical pairs that I talked about, and one of these is the one that we see here. So if we look at the handle of a let beta redex, right? So we can reduce this, this term here in two ways. We can either reduce the handle with the let by the interaction rule for handle and let that we saw before, right? The one that duplicates the handler. Or we can simply substitute v in e for x, right? So, okay, this is a reduction that may appear, so it certainly can appear in this sequence here. How should we treat it? Is it an evaluation reduction? Is it internal? Well, it shouldn't be an evaluation reduction, because clearly the other reduction for handle with let has to be an evaluation reduction. So it probably has to be internal. On the other hand, the reduction itself here cannot be internal. So it seems that we're violating this start rule down here, right? It happens in the evaluation position of a handler, but it's not internal itself, right? So the idea here, well, how do we square the circle, is we relax the rule about internal reductions, but only for handle. So the idea is, for most constructors, the internal reduction is defined in this way, right? So any sequence of reductions is internal for a let expression if we have a sequence of internal reductions on the left and the sequence of evaluation reductions followed by internal reductions on the right. And this is allowed on the right because this is not the evaluation position, right? This is the continuation of the let. Now for the handle, these are internal because these are values, right? The handlers and the value and the return values, nothing, you know, they can't evaluate. So this is fine, this is simple. And now here, in the evaluation position of the handler, the idea is that if we allow some evaluation steps, everything will work nicely, right? So what sorts of evaluation steps do we allow for? Well, precisely the ones that involve top-level let and lift. So precisely the ones like this one. And then the idea is we can follow our methodology, show transitivity of the internal reduction. Standardization is a nice consequence. Okay, so that's great. Seems like an ad hoc hack, or is it? And it seems that this is not just an ad hoc hack. It seems that there is a sort of deeper insight into why this problem appears for our particular semantics of effect handlers. And this is because the evaluation strategy that we get for these effect handlers, you know, as part of the first part of the standardization, is hybrid. And that means there's multiple kinds of evaluation context, and they treat the kind of evaluation context in which we are determines how we treat certain connectives. In this case, let and lift, most importantly. Right? So let and lift can be treated either as evaluation context formers if we are outside any handlers, or as a sort of pseudo values which we are not allowed to reduce if we are within a handler. And so, you know, these hybrid semantics, they've been mostly used for things like full normalization type evaluations, but here one comes out naturally, and you know, this is the evaluation that this reduction gives us, that this reduction system gives us. Okay, can we relate the two? And I'm sort of running out of time, so I won't go into too much detail of how we do it. But the idea is that we can define several relations and then relate the context capturing reductions to the fine-grained reductions that we've defined. One direction is simpler. The square that's on the bottom left is pretty standard. The other direction is slightly trickier. And the two main points here is, on one hand, the fact that we need to allow some sorts of context flattening to happen on the fine-grained side. This is the sort of normalization of the handler interacting with computation formers. And on the other hand, because of how the captured continuations look, there is some possibility for eta expansions. And in fact, the eta expansions that appear here cause a major trouble in the proofs. But since my time is running out, I would like to just walk over the sort of what's there in the paper, what's the main ideas, what's the main points. And the idea is that, yes, we provide a reduction theory for deep effect handlers that admits nice normal forms. The idea is that the semantics is defined by how the delimited control, the delimiter of the delimited control acts on other computation formers. We use the approach developed by Masako Takahashi and refined by James McKenna to prove the first standardization result for, or the first explicit standardization result at least for effect handlers, and show how it scales to hybrid strategies for evaluation. And we show that the evaluation in our reduction semantics matches the classical approach up to extensionality. The proof is relatively involved. And it seems that this approach to reduction for effect handlers has some nice applications, both in terms of program optimisations, this is prior work, and in terms of nice normal forms allow us to define NBE. And in the future, we'd like to try to connect this to pure lambda calculus via CPS. This is the sort of line of work from which a lot of our insights that went into this work was derived in other contexts. And possibly, we'd like to check whether this allows us to find a nice formal justification of sophisticated optimisations, which is sort of still an open problem as far as I'm aware in effect handlers. And yeah, thank you very much. And if there's any questions, I'd like to take them.
And people are also encouraged to ask questions online through Discord. And final questions, please feel free to go through one of the mic places.
Hello.
Hello, Sam.
Can you say a bit more about the challenges of extending this to shallow handlers?
Oh, so I'm not sure, so usually the difference between deep and shallow handlers is expressed by a different rule for handling an operation. And this sort of allows you to choose whether you want to duplicate the handler or not. And here, because of the fact that this is, the deep nature of the handler is already embedded in the rule for handler interacting with the let, it seems much more difficult to, determine, how shallow handlers would behave, because we don't know, like in shallow handlers, the idea would be that the handler H should handle the first operation encountered. And at this point, we don't know whether it's in E1 or E2, right? E1 could be a value, in which case the handler should be used for the continuation of the let, or there could be an operation just in E1, and in that case, it shouldn't be followed. So I don't have a clear idea how to do this. I think there are some possibilities that are sort of similar, but not necessarily quite like that. But yeah, nothing set in stone for now.
Thank you.
I will also ask one question myself. So you start this talk with a motivation where you have this program with like ask and tell, and then like statically sort of which handler is going to handle this ask. I wonder like how often this would happen in practice, because in practice, programmer often like separate the program where an operation is performed from the programmer where the handler is defined.
Well, so I think this can appear through partial optimization, where you know the definition of the function, partial evaluation, where you know the definition of the function, which is, in one module, but you still know it, and then you have some call, and if you inline the call, well, suddenly you have the ask and the handle, but you'd still. And I think this is actually quite motivated quite well in practice by the program optimization work by Karahalias and others. So that's the. I think ICFP last year, if I'm not mistaken, where they really want to have. So what they do is a proper optimization, not just simple rewriting like that, of recursive function definitions. You have a recursive effectful function, and you wrap that in a handler. And you'd really like to get rid of the handler if possible. And then, you need to figure out a really smart optimization, not just use the reduction theory, but the idea is hopefully with this sort of semantic, with this sort of reduction theory, this might help justify formally these sorts of optimizations.
Right. I guess it sounds like there's some interesting future work maybe by combining like partial evaluation and effect handlers.
I would hope so, yes.
Okay, let's thank Filip again.